Oh, he's 8.
I both those guys.
You might want to trade him on that. Why? You trade away a good quarterback to get a good player in a different position?
I'm pretty stacked.
Oh, okay, yeah,
See.
I guess.
Oh,
It's a great pleasure to be in the surrounding of highly responsible people. I was impressed how many homeworks came without reminder. But based on counting, there could be a couple of printed.
if I emailed you, do you need the printed copy?
Oh, you want to leave me no chance for to don't really.
Just trying to save a change.
Dude, I agree.
Yeah, you know, but.
Yes.
Just,
Dude, I'm trying to help the big
So, in some sort, you have taught today's class material to yourself while doing homework. So I will just summarize what you guys did here. So in what's the goal of the class? Yes, and what future of whom are we predicting right now? Huh? Yeah, electron particle in the box. So, and what is the main conclusion of that you will come to at today's class, and what you came to by the end of your homework?
There's not always an exact position, but it's a probability distribution.
Yes, but it is always so for electrons. But does this distribution stay at the same place, or something happened to it?
Expectation value changes over time.
Expectation value changes over time, and distribution changes over time. But is it always so, or it is for some specific class of initial conditions?
If an electron is in a bond,
Yes. Well, let's assume that we know nothing except for both. But we can prepare initial conditions, different initial conditions. Will this conclusion sustain for any initial condition, or only for specific? Where did we start from?
I would say it would change with the initial condition.
Yes, that's absolutely correct. But what was the initial condition for the problem that you?
but it was in between the ground state and the first excited state.
It's absolutely correct. Did you hear it? So it was neither in ground nor in excited. It was in superposition with some percentage here and there. So such states do give dynamics, do give something, some changes in time. If it will be only in ground or only in excited, it will be super boring homework. The distribution will not change in time. And the expectation value also will stay constant. Okay? So it is the main message and conclusion, and we will go through details. Details of everything. So we are at number 19. There is a chance to go up to about, well, 50, I don't believe, but 45 maybe, based on the amount of days in the year and in the class. So you are done. I will double check, but it looks like everyone completed this. And this is for the next Friday. So we didn't start it to go over the material. We just look forward, and maybe I will share something. So in the course, we do have, previous drawing was better. We have access of methods, access of systems, and access of external perturbation. No external perturbation right now, only two systems, free space and particle in the box. And for free space, we did practice Schrödinger equation, time-dependent, time-independent, and Heisenberg equation of motion. For particle in the box, we are completing time-independent. We call it done. time independent, and now it is actually your homework was on solving time dependent Schrödinger equation for particle in the box. And main message that we already discussed right now, that for time dependence, it is critically important to know initial condition, right? Because the conclusions, the trends, what we will observe for the same system will depend on initial condition, which is not a big surprise. If we play billiard and suppose that we do not consider them anyone winning, any ball coming to corner, they're just moving and reflecting. So the trajectories will strongly depend on who and where will kick. But the balls are the same, the box is the same, right? Yeah, this is time independent energy with different wave vector inversely proportional to size of the box, and energy, wave function and energy. Denominator with size of the box, and in the denominator number, index of the energy squared, right? Later on in the course, or if you will be exposed to any quantum problems in other circumstances, you'll see that for different quantum systems, one can also label solutions with the index. But typically, so n squared is growing function. So it's make state becomes sparser and sparser. But for most of quantum systems, it will be denser and denser. So this dependence will be not power, but something like 1 over n squared if you were exposed to hydrogen atom. Just move to the future in month. So suppose, I don't know, is it right or wrong? Suppose that you hate math. Suppose that you hate any equations, but there is a necessity to deal with physical chemistry, quantum theory, and particle in the box, or maybe some other quantum systems. You already know. We do not need to be mathematically educated to accept an idea that an equation has many solutions. We do not need to be mathematically educated to accept that there is a set of functions and there is a set of eigenenergies, right? Simple. But if I do not have energy to write equations or memorize them, but I need to get general intuitive vision of the solution, what would you do? Probably hand waving, like there's a box and the probability comes up and down, that's it, right? And if it comes up and down more often, the energy is higher, right? So does it sound intuitive? You can speak this language without any equation. So it is pretty standard representation and figure that people are using in the textbooks. So you know that one is not expected to add together apples and oranges, but many authors of quantum theory books do. So they add together energy and probability. If you are rigorous, you would probably dislike it, but for visual representation, you put x-axis as your position in the box, and on the y-axis, you put simultaneously the shape of your wave function and offset of the energy. Because if you plot them all together, you're going to go a couple of slides. If you draw more than 2 or 3 lines, they will be clogged. They will block each other, and you will be not able to follow what they are on one hand. And on another hand, if you combine both spatial distribution and energy in one figure, you kind of get intuitive picture that you can memorize visually and intuitively interpret some situations without writing equations and guess answers immediately. So develop some expectations, which is really important. So if we are not going to become professional theorists or computational chemists, we may forget equations, but intuitive development of intuition for expecting how systems will behave is a take-home message that probably will stay with you a little longer. And same for the probability. If you have this stuff squared, you just offset the figures from zero, from the origin by the size of the energy. Right? Where zeros will convert into zeros, where there were either maximum or minimum, will be always maximum because it is squared. Okay. Now, how do you create a superposition? What do you do to have this half excited, half non-excited? Any ideas? Who was speaking about Schrödinger cat? Okay, so this is the same situation. It's like half dead, half alive. So how it is prepared? Any ideas how we can prepare it in the lab? Well, this is a really challenging question, and it's many people do not have the answer. But I know one of the answers, which maybe not general. If you know that sending one quantum of light will promote system from ground to excited, right? Then we can think back that light is oscillations of electromagnetic field, and we let them oscillate for a specific duration. So if electric field induces transition, it oscillates, and it induces transition. Not instantaneously, but slowly. And if you suddenly stop this inducing electromagnetic excitation, it may not be ready to go up to from ground to excited. So it's irradiation by resonance electromagnetic field by shorter time, twice as shorter time compared to what is needed for full excitation. So did anyone turn the knobs or operated through keyboard with NMR device? Was it in your lab? So in the NMR, they also have ground and excited states, but they are of very small energy offset. And there, the radio frequency performs this excitation. So functioning of NMR device is based on creating such superposition. So suppose we have 50-50, and then we look on what will happen with the wave function. Sometimes one utilizes so-called Dirac notations, and if you didn't cover them, we will cover them later in more details. But there is as we go through the course, you will see more and more, and you were already exposed that there is a symmetry, there is a connection between functions and vectors, conjugated functions and this row vectors and column vectors, right? And if we want to be super abstract, non-specific about whether it is vector or function, just quantum state, Then people do this angular brackets. So we have our ground and excited. We have we superimpose them with 1 over square root of 2. And someone who helped with designing this, it was one from the class. Or maybe if no one wants to take glory for this, it was collective effort. So if you do want probability to be 50-50, and you know that probability is getting by taking wave function or expansion coefficient squared, then if you have square root of 1 over square root of 2, when it is squared, it gets 1/2, 50%. Therefore, it is square root of 2 here and there. Any questions or objections?
Just to clarify, the weird like line and then bracket just means a superposition, right? Around like a 1 and 2.
No. We just replace good normalized wave function by this notation.
Okay.
If I do not want to write this phi, if I have forgotten Greek alphabet, or if I know I knew it. Okay. So please do not hesitate to stop, because I can close eyes, forget about you, and just enjoy the material that you probably do not want to. So, yeah, see, I'm closing the eyes. How do we predict future? By words, without equations. What is the main idea in the protocol to predict future? I'm inviting you to do the standard well, for some people it is a main skill in this course. I do not think so, but it is one of the, to translate mathematical language into human words and translate human words into mathematical language. So how do we predict future by human language? I already noticed that this question freezes the whole class. No? No ideas?
You get an initial condition and then propagate the wave function through time.
Yes, exactly. And what is the mechanic of this propagation of wave functions through time?
Time-dependent Schrodinger equation?
Yes, and we already know how to solve it. So our way to predict future is, in some way, it is explanation how to solve time-dependent Schrodinger equation. So please participate in this discussion, or just listen, because this will come up again and again. So each eigenstate, each eigenfunction, propagate in time by accumulating phase according to its energy. Make sense? So if you had a wave function in the past, eigenfunction, not any, but eigenstate. And in the future, they will be different by e to the power with energy of the state in the power of exponential, with the rest garbage, like imaginary unit, time divided by h bar. So propagation from past to the future by exponential with energy of this state. But each state, if there is no degeneracy, each state has its own energy. So each state will accumulate different phase as we go from past to the future. So it's one thing. And another thing is that our true initial condition, our true state where we start from, is combined of eigenstates at different proportions. So two things. Take into account different proportions, which we call expansion coefficients. And second thing, each eigenfunction accumulates different phase or accumulate phase at different pace. Phase, pace. Right? Phase, pace. So those are our eigenfunctions. Those 1 over square root of 2 were initial conditions. We just decided that it will be halfway between ground and excited. And those are actual phase accumulation. So for the state 1, it is I something energy of state 1. For state 2, it is I e to the something energy 2. Okay? So maybe it takes time to digest and get comfortable, but we will come to this again and again. To predict the future, we need to take into account that each eigenstate accumulates phase with different pace. Okay. Now, if you were thinking intensely, you can just lean back and relax a little bit. I'll give you a sign when to wake up and concentrate again. Well, who needs all these solutions? Well, it is a philosophical question. Some of you may decide that no one needs, so that it's only exercise for torturing your minds. But if you, this is a model that a protocol model that we in class or later in the big life will repeat for predicting observables, predicting properties, for characterizing the true models. So wave function itself is not an observable. You do not measure it typically. Some crazy people try to, but it's not standard experiment. An example of simple observable is the position, expectation value of position. So we find wave function as it develops in time only with the purpose to find some observable. Or if we are not ready for observable and we just want to get intuitive vision of what is going on with the system, we may think on probability distribution, which is wave function squared. So the wave function itself is not very much useful. It is only an intermediate step to get an observable, and if you want to get to entertain ourselves with intuitive understanding of the system, probability distribution. So what do we do with wave function if we do need probability distribution? I don't believe that you have an idea. You probably just say like, you're getting so. Go ahead and entertain us. You just sit and listen. So, give me a sign if you do not know how to convert wave function into probability distribution. I was right. Everyone knows.
Do you just multiply it by its conjugate?
Yes. Yeah, that's right. So if you know wave function, and basically it is our future, we already know, right? But it is not useful. We need to wrap it up in a better shape, better form. And one of the shapes that has a little bit of use is multiplied by its conjugate, right? So there are two terms, wave function conjugate. Each term has, each factor has two terms, right? Because we skipped second, third excited, we will be dealing with only with ground waves, otherwise it will do more. And if you multiply two factors with two terms in each, what will be the total number of terms in the result?
1.
Yes! I've got the interaction and engagement of class into the discussion. Thank you, Alex. So the terms, and you see, in this future, in this prediction of the future, I'm going to scroll back and give one little technical announcement that we will appreciate later. So, in fact, the factor in front of eigenstate is initial expansion coefficients times phase accumulation, right? But we can combine them together and tell that right now we still have an expansion coefficient, but it already includes time dependence. So we have time dependent expansion coefficients. And then it will be just much easier to process things. Many times there are no mathematical challenges and there is only calligraphical challenge that you have to repeat similar terms again and again and follow them. And if you simplify, it's better. So this C1 and C2 includes initial, this 1 over square root of 2, each of them multiplied by phase accumulation. Whew, good. Now, for probability distribution, we will need to multiply two factors, two terms in each. And upon opening the brackets, we will have 4 terms. One term will include eigenstates, and one factor in each term will include eigenstates, and another factor will include time dependence. Right? So just carefully opening the bracket. And the eigenstates will be coming in pairs, and they can either coincide or not coincide. Like first and first, second and second, or second, second and first. Right? Not very challenging. Same pattern for this time-dependent coefficients. First and first, where one is conjugated, second and second, and then this cross terms. First, second, second, third. Good? And we do know that this time dependence is nothing but exponential, imaginary exponential with energies. And we know that when we put star, it means we flip the sign. Okay? Do not wake up, still relax. I'll give a sign when it will be really important. So if I'm looking on the first term and only the factor that explains time dependence, I just look inside what I imply under this notation. So for one of these C coefficients, it will be e to the power minus I energy, and for another it will be plus. And if you multiply two phase accumulation factors that develop with the same pace but in opposite direction, what would they be? Yes. So when the numbers are equivalent, first and last, there will be no time dependence. Keep sleeping, keep sleeping. I'll give you a sign when I will summarize. We shouldn't spend too much mental efforts. So if the indices at the bottom of these coefficients coincide, if it is the same energy, n equals either 1 or 2, both cases, then it will be developing accumulating phase in one direction and then same phase but in opposite direction. And these two exponentials will cancel each other, right? Because e to the power x, e to the power minus x will be 1. Convincing. What if the indices will not coincide? Bless you, bless you. Bless you, bless you, bless you. So what will happen if indices do not coincide? Too bad, things do not cancel and we will still have the some sort of phase accumulation. It will be all this constants, time, and then energy difference between participating eigenstates. So when we convert our prediction of future into observables, we will have time accumulation in two forms. Either no time dependence, just cancel, or accumulation of phase according to difference of energies. Not too important. I'll give sign when it will be really. Yes.
Question: does it matter which one of the coefficients comes out or not?
Which is second? Yes, if you accumulate phase positive or negative.
Okay.
Therefore, we have these cross terms come twice. 1, 2, 2, 1, and star is in front of 2 and in front of 1. I'm going to answer your question. I'm going to travel through the slides to the very first slide, show something there, and then return back. So close your eyes when I will be traveling because it will be boring to see all. So here is the whole work and the code that you did practice. Look at the first line right after declaration of site. So it has this RR, 1/2 R11, 1/2 R22, and then R12 times cosine. There is no imaginary things, only the real part. I'm not expanding it because you already know what it is. So for time dependence, you have cosine, a real function. So this answer to Alex's question. Alex asked, does it matter in which direction phase accumulation develops? There are terms, two terms. In one, phase accumulates forward, and in another backwards. But when we add them together, our old buddy Euler helps us. Two exponentials developing in opposite direction after summation give cosine. Okay? So in some sort, today's lecture is the background for the homework that you have already completed. And I'm trying to bring this. Now close eyes and wait until I find the right slide where we stop. Somewhere here. Yes. So probability distribution. There shouldn't be star here. Remove one star. Wave function with star, without star, and then this 4 terms. Wave functions, time dependence. Wave function, time dependence. Product of wave function, time dependence. Maybe if you have relaxed a little bit, it's time to slowly wake up. And do not hesitate to stop me, because there is no reason to go forward if you don't follow. So, if we are looking on probability distribution composed as product of the predicted future of the wave function, then there will be 4 terms, each term consisting of 2 types of factors. One factor is product of 2 wave functions, another factor, time, is product of 2 time-dependent expansion coefficients. And those who were following, the time-dependent coefficients are trivial if indices of this wave functions coincide. It is so-called diagonal indices, and there will be phase accumulation if they do not coincide. The products of functions will be just eigenfunctions that we have already found, like sines with specific wave factor. If it is 1 and 1, it will be just sine of the same sine squared. times itself. The following statement has no science in it. It's only notation to save time and reduce calligraphic challenge. If you do have product of the time-dependent expansion coefficients, it is too many symbols to write. C, 1, bracket, T, bracket, C, 1, star, 1, bracket, T, bracket, about a dozen symbols, right? We can write twice as less symbols. Just call it symbol row and put these two indices, row and 1. Just redefining, giving new notation to save calligraphic effort. So this and these factors will accumulate everything about phase accumulation, and it is critically important for predicting fusion. Okay. Now let's put together all things. Just open what they mean. So product of first wave function, product of second and first and second, second and seconds. And this products of wave functions, we will call them rho. This is a Greek letter, rho. Same as Latin R. You have seen it probably in the density, in Archimedes. So rho 1, rho 1, 2, rho 2, rho 2. If indices do coincide, we have exponentials developing with appropriate energies in opposite direction. Plus and minus cancel, give no time dependence. Rho to 2, accumulation of phase forward and backward, cancels, gives no time dependence. But if it is off diagonal terms, by the way, see, it looks like a matrix with two indices. You can probably put it just 2 by 2 matrix. So those will be diagonal, those will be off diagonal. So if these off diagonal terms are processed by this energy difference, you will see that there will be time dependence, but it will accumulate in opposite direction. Right? So energy difference defines accumulation of phase in these elements of density matrix. Good. And now we come back to your gloriously completed homework. So remember these notations, R11, R22, R12. Those were these products of wave functions, right? So if it is index is the same, it was just a probability distribution for ground state, right? Wave function multiplied itself with probability distribution. This for ground. I need to match the color. Ground. Then the red with two humps, it was excited, right? So if you have wave function times itself, it will be just sine squared. Nothing negative, camel with two humps. Right? And if you multiply this off-diagonal non-coinciding wave functions, the ground state is always positive, but the first excited goes positive and negative. Therefore, product has some negative part. But since there is no imaginary part for the ground state, the two off-diagonal terms, 1, 2, and 2, 1 will coincide. The yellow and purple here. Okay? So these spatial distributions, these four functions, will be added together with different expansion coefficients, where expansion coefficients do depend on time, or may or may not depend on time. So therefore, in your coding homeworks, they just brought up to show what is going on. That's it. Okay, and if you add them together with, probably I should write something. If you add together rho 1, 2 plus rho 1, 2 times this sine 2x sine x plus rho 2, 1 sine x sine 2x. I'm just skipping the constants. Rho 1, 2 and rho 2, 1. We can put the spatial part out of the brackets, and rho 1, 2 plus rho 2, 1 will be added together. Sine 1x, sine 2x. And if you plug in that those are accumulation of phase in the opposite, T2 minus T1 times T plus E to the power minus I over H bar E2 minus E1 T. So this summation together will result in 2 times cosine E2 minus E1 by H bar multiplied by T. So this explains why we didn't have any imaginary accumulation of time in the code. So it was the diagonal terms when sine x squared and sine 2x squared were just contributing at each instant of time without any time dependence, and the cross term was coming with factor equals to cosine. And when we added together these terms, doesn't want to if we add together all these terms, then you see the same thing which you observed while doing homework. So two functions of ground and excited are either added together or subtracted with these off-diagonal terms which oscillate, right? And now you see the mechanics of this time dependence. So we just add together products of wave functions weighted by different time-dependent coefficients. But as a result, you do have an interpretation that your particle in the box bounces forth and back between walls. Make sense? I think I'm done. So, end of the meeting. Please approach and ask any questions, but I'm looking forward to see you on Monday, and have a nice weekend. Yes, favorite spot.
Alright, can you go back to the boundary one?
Huh?
Can you go back to the boundary one? So you don't have
When the Eagles Vikings are here.
Get 3:30.
Really nice. So we'll-
30-minute nap.
I'll be able to watch the summer actually. Hopefully.
Yeah.
Here's a party at my house.
So then this
Parastar?
Yeah.
It's one of the, yeah, it's one of the.
2 times
But you
cosine.
can totally tell when it's gonna be.
We're on the
There's
street,
no
like,
chapter
map.
or like-
Next,
See you
like,
later.
taxes.
So the time dependence comes from the cosine.
Yes.
Okay. So, an Euler's formula gives us that?
Yes, this is Euler. So in fact, we are getting this product of sine and cosine times adding together this
adding
time
that
dependent, and they're coming as summation.
Yep, I see why Euler gets us that now. It was really
What?
why this becomes Euler, because I thought this was multiplying for all like always going through. So
No,
if
no,
you,
no,
if you
no,
multiply it, I'm like, shouldn't it just equal like 1? That's why I was getting super confused. But I see that you're be adding them, and then you use the trigonometric function.
Is this still sine?
Yes, yes.
Okay, so it is multiplied that.
Yeah.
And then that's the oil. Okay.
So guys, please stop me, because I hope you can speak the same language, but it's something that for me seem very simple, maybe hard for you. Some things that I consider like complicated, maybe like snap for you, because young brains work quicker. So I'm spending many time on primitive math, which you may already know, and skip major concepts. So you're doing a good job of stopping. Keep doing so.
Because I'm like, I like to see all the calculations like almost drawn out, because then I
Yeah.
can actually see where you're going with it. Sometimes
True.
Sometimes I can get where you're going if you skip a couple of things, but
Or an explanation of what or multiply. Like, what does this mean?
so if we were to take that cosine out, the cosine function out, it would just look like the original sine function that you had in with the dotted lines,
Yes.
and it would not change if time was to change.
Yes.
See you, Bill.
So we add together this three functions.
Uh-huh.
The blue and red are coming with the same, with a factor 1. They don't change in time. But these dashes will come with cosine factor. So it will become from positive to negative. It will be changing up and down. Therefore, it will shift the average distribution. So right now it will cancel this red stuff and enhance red stuff there. So it will be moved there. But if we travel by half period, it will increase this one and depreciate this one.
Oh, okay. And you said that they were multiplied when you get the bouncing function, or is that addition?
This one is multiplied by cosine of delta E times T. And those are constant.
Okay. And so to get the bouncing function, that you're adding all of these probabilities together.
Yes.
Okay.
Add these three functions with red and blue come just as they are,
Mhm.
and the dashed one comes with oscillating factor.
Okay. That makes sense.
That's it.
Thank you.
Yeah. Thank you.